Hi students, welcome to another video on analog electronic circuits. In this video, we will have a look at the differential amplifiers. Before we start, so just go through these few slides. These are the basic things you should know before we start this differential amplifiers. You should know Kirchhoff voltage law, Kirchhoff current law, basics of MOSFET, and how to write the AC small signal model of MOSFET and CS amplifiers. Of course, you need to be dedicated while watching this video. A notebook is a must. If you have few colored pens, it is good. And of course, your attention is very much important in order to understand these concepts. Of course, minimum of half an hour uninterrupted time is required for understanding differential amplifier. Pause the video whenever you are not getting it. Just rewind it. Make sure that you understand the concepts. If you are ready, we'll start. So now this is a differential amplifier circuit. Some of the assumptions what we are making here is two MOSFETs, whatever we have, two MOSFETs M1 and M2 are assumed to be identical. When I say identical, their W by L ratios, W by L of 1 is equal to W by L of 2. Their threshold voltage of VTH of 1 is equal to VTH of 2. And of course, whatever Kp that you have for both the MOSFET should be same. And of course, mu n, okay. All parameters should be same. Suppose if you consider this has some channeling modulation, that should also be same. Lambda 1 is equal to lambda 2, and we are also assuming that resistor connected to drain is same RD. With these assumptions, let us start the analysis. Now what we are considering here is, so these two are the two MOSFETs, and I have a current I which is being applied to the source coupled point. Okay, both the sources are coupled here, and we have connected a current source I. So since these two are identical in all nature, the current that is flowing through this, suppose if I say this as ID1, which will be half of I. Suppose this is, if you name it as ID2, this is naturally I by 2. So this is the current that is flowing, and we have we are having two inputs, V in 1 and V in 2, and we have two outputs here, V01, V02. So of course, let us try to identify some terminologies, something like differential input, single-ended input, all those things. So this is single-ended and differential. When I say single-ended, because for any voltages to be applied or measured, you need to have the plus terminal and the negative terminal. Suppose if the negative terminal is ground by default and the positive terminal is the point which you are considering. If the negative terminal is ground, then I'll call it as it's a single-ended input or output. So now suppose if you say in this particular case, which is a single-ended input, I can say V in 1 is a single-ended input because this input voltage is V in 1 with respect to ground. So this is a single-ended input V in 2 with respect to ground. So since the reference is ground, the two single-ended inputs are V in 1 and V in 2. Because you are measuring, you are applying the input voltage with respect to ground, you are applying the input voltage with respect to ground. So that's what is two. You have two single-ended inputs, V in 1 and V in 2. So similarly, you have V01, V02. So again, you are measuring this output voltage V01 with respect to ground. You are measuring this V02 with respect to ground. The two single-ended outputs are V01 and V02. That's what you mean by single-ended signal. So this is a single-ended signal. That signal can be input or output. So we have identified which are the two single-ended inputs and which are the two single-ended outputs. When it's come to differential, here also you have plus minus, because you consider any voltage for that matter, it will have a plus and minus. Suppose neither of plus or minus is a ground. So now I'm not considering the ground at all. Suppose now if you say, if you are applying an input voltage between this and this, suppose in that I'm just applying some input voltage between these two things. So then I'll say this is a differential input. So there is no ground mentioned here. So this is called as a differential input. So if I apply between these two here, and so this is, suppose if I'm applying input voltage which is not having a reference of ground, so then it is differential input. And suppose if I measure the output voltage, this as plus and this as minus, so now this is a differential output. So because this is output, V02 minus V01 is differential output, or V01 minus V02 is a differential output. These are the two possible differential outputs. So what is the differential input? V in 1 minus V in 2. So that is this. So suppose if you are measuring, if you are applying the voltage between this and this, or between this and this, so then that is the differential input voltage. So that's what we have, something like single-ended voltages and differential voltages. So that's about the single-ended, that's about the circuit configuration. And we have two supplies, one is VDD and other is minus VSS. So this is a dual power supply, it uses a dual power supply. And interestingly, you can see for this differential amplifier, against the CS amplifier, we usually used to have potential divider biasing and then something like this coupling capacitors. So all those things are not there in this differential amplifier. Let me just take this. So now this is a CS amplifier. You have RD here, you have R1, R2, CC. So these are all required for biasing and applying the input voltage and coupling this. So now if you can see here, so there is no need of any potential divider biasing. This minus VSS will itself, and of course plus VDD itself will provide the required biasing for this. And there is no need of coupling capacitor here. There is no need of coupling capacitor for a differential amplifier, neither here nor here. So that is not there in case of a differential amplifier. So this is the biggest advantage of differential amplifier. It is not having a coupling capacitor, which is so advantageous in terms of its frequency response. But I've seen that while discussing the frequency response in the last videos, we have identified this one. So this frequency response, which is this part of the frequency response, is decided by this CC. So this whatever cutoff frequency F1 you got, it is coming from 1 over 2 pi R in CC. Suppose if this CC itself is not there, then this will have something like this type of frequency response. So there is no cutoff frequency here. Meaning a differential amplifier will not have this CC, so that it will not have this cutoff frequency at all. The frequency response of a differential amplifier will be something like this. So if I write just for clarity, this is your frequency, this is gain in dBs, so it will be like this. So it will be having a flat response from the beginning itself, and then it goes. And of course you'll have 3 dB bandwidth here, this is so and so, you can see, but this is a constant. There is no pole here, sorry, there is no cutoff frequency here, so this is going to have a gain of some whatever the gain. So this is the advantage of not having a coupling capacitor. We call this as a DC gain of the amplifier, DC gain of the differential amplifier, which will be having no lower cutoff frequency at the lower frequencies. Okay, with this we move on to try to identify for what how does this amplifier behave for a differential input, how does this will behave for a common input, all this stuff. So let me rewrite that differential amplifier. So this is a differential amplifier what you have. Please do write the differential amplifier, and here this is my current source. This is minus VSS, this is VDD, and let me take this as RD, this also as RD, this is V01, this is V02. Let us take differential input voltage. So let us take it as this is VID by 2 and this is minus VID by 2. I'm applying same magnitude to both of them, but one is plus, other is minus. So it is a balanced differential input. The input is differential because these two are different, but it is balanced in terms of magnitude. So this is called as balanced differential input. If the input is like this, let us try to find out what is V01 by VID. So what is this V01 by VID? So this is, so now I want to find the gain which is measured single-endedly. So it is, I'll call it as ADSE. That is, it's a differential gain with single-ended measurement, ADSE. So I will also have V02 divided by VID, which is also ADSE. The output is measured here with respect to ground. The output is measured here with respect to ground. That's what is differential single-ended output. Single-ended output. This is differential because the input is differential. Input is differential. The first suffix indicates that input is differential. This indicates that output is single-ended. Output is single-ended, meaning this is measured here with respect to ground. Of course, since you have two single-ended outputs, I'm going to have two gains. One is ADSE, other is also ADSE. This is V01, this is V02. And we will have one more thing, which is V02 minus V01 by VID. Now, how you are measuring the output voltage? Output voltage is between this and this, So since it is between the two output terminals where ground is not involved, I will call it as a differential input, differentially measured output. So what is this here? This D stands for input is differential, whereas this T indicates that output is measured differentially. What do you mean by measure differentially? When I'm measuring the voltage, output voltage, I'll just put plus here and minus here. Then this is a differentially measured output for a differential input. So that's what is a gain, which is differentially measured for a differential input gain. So let us first start with ADSE. So now whenever you apply some signal, so we know that this M1 M2 will have some dimensions, they'll have KP and all those stuff. So let us assume that M1 is having a transconductance of GM1 and M2 is also having a transconductance of GM2. Since we are assuming both of them are identical, I can write GM1 is equal to GM2 and that is equal to, let me write it as a common term, GM. So now what is the current that is flowing through first transistor? What is the small signal current flowing through this? Because you're going to have two currents, one is capital ID, other one is small id. So let me write it as capital ID1 and small id1. If I say this is my current I, let us assume that, so there is a resistor associated with this current source. Let us say this is RSS. if it is RSS and if this is I, the current ID that is flowing through this, that is the DC current, will be I by 2, half of this, and this ID1 will be equal to GM1 times VID by 2, because we know that whatever current flows in the MOSFET is due to the input AC voltage multiplied by its transconductance, which you can write it as Gm into VID by 2. VID by 2. So what is the direction? Direction is going this way. So this is the direction of the current. Similarly, what is the current that is here? So what is this is now ID2 plus of small ID2. So this ID2 is now due to this input and its transconductance is this. So what are the transconductance? The transconductance is Gm to what is the input? Input is minus VID by 2. Input is minus VID by 2. So now since Gm1 equal to Gm2, you're considering it as so and so. So now what is the current that is flowing now? The current that is flowing is minus Gm VID by 2. So this minus Gm into VID by 2 is actually, this is the current that is flowing here. So the current that is flowing here is minus Gm into ID by 2. Instead of seeing this current as negative, I can say this is having a magnitude same as this. So suppose if I say this as some Ix. So what is Ix? Ix is actually equal to minus of ID2. So suppose if I consider this is ID2, this is ID1. If I say this is Ix, so Ix and ID2 are going in opposite direction. What is Ix? Ix is actually equal to Gm VID by 2. If you can carefully notice, whenever the applied voltage is balanced and of same magnitude and but out of phase, whatever current that is flowing here, the same current is flowing back here. Meaning that as per your KCL, Kirchhoff current law, if you write it at this node A, this is one current, this is other current, this is the third current. So this is what I'm calling it as a small AC current. If I say this is what IA, IB, IC. So what is at node A? So as per your KCL, applying KCL, so current IA is current that is entering, that is equal to current leaving is IB plus IC, correct? This is what your assumption is. So this is a current, this is a current, this is a current. What is IA? IA is actually equal to this ID1. I want to know what is IB. So what is IC? So IC is actually IX. So IC is IX. So what is ID1? ID1 is GM VID by 2. This is equals IB. What is IX? IX is actually this. IX is minus, this is actually GM into VID by 2. You can see now this is GM into VID by 2. This is also GM into ID by 2. Then what is IB? So IB is actually 0. Meaning there is no AC current flowing here in this. Meaning the current that is flowing through this, the AC current, the IX is 0. Whatever current that is flowing here is 0. So from this, what we are trying to understand is whenever you apply a AC voltage which is a balanced one and differential, VID by 2 minus VID by 2, whatever AC current that flows here will be going back in this direction. So zero AC current flows through this RSS. Zero AC current flows through this RSS. So if I write the AC equivalent of this, I can write it this way. So we know that this is actually VID by 2, and this you can AC ground it. This is now this, this is M1, this is M2, this is RD, this is RD, and of course this is treated as open circuit. For AC analysis, this is AC analysis. For AC analysis, you are shorting the voltage supply to DC to 0, and all AC currents will be open circuited. So this is your DC current you open circuited, and this is grounded, and you have this as RS. This is RSS, this is ground. Now you can see whatever current that was flowing through this, the same current is flowing back here. So now the current is actually 0. When the current is 0, the voltage reference is also 0 volt. So when it is 0 volt, this is ground. When there is no drop is there, what the voltage you'll get? You'll get 0 volt here also. If this is the actual AC ground, this is the actual AC ground. So but even though you have a resistor, since the current flowing is 0 here, since the AC current flowing is 0 here, the voltage here is 0 volt. We call this particular source coupled point as now virtual ground. This is not actually grounded, but virtually it looks like a ground. So this is virtual ground. So now this is V01, this is V02. So what is the circuit now? The circuit looks like this now. For an AC signal, the circuit is now looking like this. So now you can as well eliminate this because this is ground. So when this is ground, so there is no significance of this. So then this circuit becomes this. So I can write it as a ground here. So this is VID by 2. This is ground. This is V01. This is RD, and so on. So can I ground this also? This is minus VID by 2. This is ground. This is RD. I want to find V02. So what is the current that will flow here? It is ID1. So what is the current that will flow here? It is ID2. What is ID1? It is VID by 2 into GM. ID2 is minus VID by 2 into GM, because we are assuming GM1 equal to GM2. But what is V01? V01 is the current that is flowing here and its drop. So I can write V01 as minus of ID1 into RD, because this is actually the current what you are supposed to find. So I can write it as I0 into RD, which is nothing but minus ID1 into RD. So what is V0? Okay, from this can I write it as what is minus VID by 2? So you have this is now minus VID by 2 into GM into RD. So this is what is V01 by VID is equal to minus GM RD1. Similarly, what is V02 is equal to, if I write this as some I0, is it not I0 into RD? What is this I0? I0 is actually in the same direction. So now what is I0? I0 is actually minus of ID2 into RD. What is ID2? ID2 is actually negative. So negative of negative is now VID by 2 into GM into RD. This is V02. This is V02. If I take this VID here, this is GM into RD. So what is this? What is this? This is what we are looking for. This is what we are looking for. We were looking for V01 by VID. We got V01 by VID. See here, this is what we are looking for. We were looking for V01 by VID, which was ADSE. The output measured at this point, considering this as the, of course, this is minus VID by 2. If the output is measured here with respect to ground with these inputs, so it is minus GM into RD by 2. If it is measured here, then you can see it is okay. Sorry, this is plus gm into RD by 2. So this is what? This is also ADSE. ADSE. So there are two differentially measured single-ended gains. One is here, other is here. Here it is out of phase, but here it is in phase. Here it is in phase. Suppose I hope okay you got this. This is ID1, the current flowing here. ID2 is current flowing in this direction. Since it is minus, you have it as minus VID by 2 into GM. Since it is plus, this is actually input, AC input into its GM. Since we are assuming GM1 equal to GM2 equal to GM, so I'm just writing it as GM here. And you're trying to find what is V01, which is the voltage drop across this RD. So I'm considering this I0, which is actually in the direction opposite to this ID1. So that's what we wrote it here. I0 into RD is nothing but minus ID1 into RD. So it comes this. And similarly here, what is this V02? This is actually V02, which is ID into RD, but this ID is minus of ID2 into RD. But this minus of ID2 is what you have. So since ID2 is negative of this, minus of minus this, VID by 2 into GM. So you end up with this as your expression for differential input single-ended gains. So this is single-ended measured and differential input gain. Suppose you want to know what is the gain of a single-ended differential input, but it is measured single-ended. Sorry, measured differentially. So we need to find this. We need to find this. We know what is V02. What is V02? This is actually VID into GM into RD by 2. What is V01? It is minus VID into GM into RD by 2. So now if I do V02 minus V01, so now what will happen? So does it be VID? Can take this out, minus of minus will become plus. Will it not be GM RD by 2 plus GM RD by 2? So what is V02 minus V01? Is it not VID into GMRD? So what is V02 minus V01 by VID is actually GM into RD. So what is this? What is this? This is actually differentially measured output voltage. This is a differential input. So shall I write it as ADD? This is my ADD. So differentially measured for a differential input voltage gain. So voltage gain of a differentially measured differential input. So it is GM into RD. So this way you can able to easily understand the gain of a differential amplifier for a balanced differential input. But of course, this is true even if you apply what all equation that we found. So it is true for unbalanced differential input. So let me try to tell you what do you mean by unbalanced differential input. So assume that this is your differential amplifier. This is RSS, this is minus VSS, this is VDD, and this is so on so. Now let me ground this. Let me apply entire VID here. This is RD, this is RD, this is V01, this is V02, this is M2, this is M1. Only thing is that instead of applying VID by 2 and minus VID by 2, which is a differential input, now it is balanced differential input. Now it is unbalanced differential input. Why it is unbalanced? Because over here you are giving 0, here you are giving VID. So that's what is unbalanced. Why it is differential? But it is why it is differential is here you have different, here we have different. So that's why it is unbalanced differential input. The gain expression for ADSE and ADD remains the same as we did it for a balanced input. So this expression for AD, SC and ADD remains the same. So but when you are having RD same and both the transistors are identical, even you apply a differentially balanced input or differentially unbalanced input, the expression for ADAC remains the same. So this is one key parameter you should remember. Okay, details of this is available in one of my previous videos. You can just have a look at it. Otherwise, whether the input is balanced differential input or unbalanced differential input, the expression for ADSE and ADDSE remains the same. So this is the expression for ADSE and this is the expression for ADD. So this remains the same. Here it is in phase, out of phase, and this is in phase for a signal which is either applied balanced or unbalanced input. Okay, we will see other common input as well as the CMRR of this differential amplifier in the next video.